here's what the problem was. The problem was, in general, if you take a point and you want to find a line that's tangent to the curve, then you might have more than one solution. There might be more than one thing that you can do to draw a line that's tangent to that curve. As an example, you could think about some geometry you've seen where if you have a circle and you think about lines tangent to that circle, then there's two of them, right? From any particular point. You've seen some circle theorems about those lines. And similarly, if you just take the point A and you think about lines through that point that are tangent to this curve, there's more than one. There's the line like the one they've drawn, and there's also a line with a kind of steeper gradient that's tangent down here somewhere. The question doesn't specify whether we need to know, are we supposed to have B bigger than A or B less than A? So I did what seemed like a simple thing. I went back to the person who was around in 2011 and was involved in writing this question, and we had a chat about it and eventually agreed that the question should have specified that B was greater than A. The question is supposed to say that B was bigger than A, so that we're in this sort of case like the one in the picture where B is to the right of A, and then you get a region over here. And if I'd struggled through the question and got down to part 5, I'd have found that, well, if I was down at part 5, then maybe that doesn't make so much sense. So the question should say somewhere, question wants also, by the way, this is how you fix it, also by the way, B is bigger than A. Okay, so that's the fix to the question. For the people who weren't here last week, I'm going to speed run through the first couple of parts, and then we're going to talk about parts 3, 4 and 5. Use the fact that the line and the cubic touch when x equals b, and that means they've got the same gradient. We've got an equation for the cubic, so the gradient there is 3x squared minus 1 at x equals b. That's supposed to be equal to the gradient of the line, which is m. Okay. The line is y equals mx minus am, or I should maybe have written that as ma, so I've just multiplied out this bracket. So this constant in the line here is minus am. Okay, why have I done that? Well, I suppose I also know that the line is y equals so y minus like the y value is equal to m times, or I know m, x times the x value. I know that the line has gradient m and it goes through this point b cubed minus b. Okay, so compare the constant terms, and compare the, what's that called, x-intercept or something. Compare the x-intercept when y is 0, and you get something like minus am is equal to, and then on the other hand, the equation over the x-intercept over here is going to be b minus b cubed or something. I'm putting in y equals 0, b minus b cubed over m plus b, or something like that. That's the x value when y is 0. I think I might have the x value when, the x value, the x-intercept is a. I'm being silly. Okay, so that's the value of a. I think if you rearrange that, things work out quite nicely, and it turns into this value of a. Okay. So if a is very, very negative, if a is minus 1,000,000, when does that happen? What's the approximate value of b? And the trick is to look at this expression and say, when is this very negative? Okay, so here's the expression. I want to know when is that very, very negative. And while also knowing, I suppose, that b is going to be somewhere around here on the curve. So b is going to be somewhere between -1 and 0. Thinking about how this line meets in its tangent to the curve. Okay, so when is that very, very negative? And actually somebody in chat said, I think the right idea last time, that this fraction becomes very, very large, either positive or negative, when we get to a point where 3b squared minus 1 is about 0. Because if we're close to 3b squared minus 1 being 0, then this is something divided by something that's almost 0. So we'll get a huge answer. Okay, and I suppose that if 3b squared minus 1 is positive and b is negative, then a will be, the answer here will be negative and huge. So it'll be like minus 1,000,000. Okay, so that's the point with b is roughly 1 over root 3. Okay, or I suppose minus 1 over root 3, careful about squares. And actually it is the minus 1 over root 3 that we want, isn't it? Because from the diagram, b is somewhere between minus 1 and 0. Okay. I suppose I know that because the gradient of the line, they have told me that the gradient of the line is positive. So this line which goes from A over here somewhere must go upwards and touch the curve over in this section over here. So that B is between minus 1 and 0. Okay, so there's a part of this question here which says, okay, great, we haven't thought about C yet. C is this other point where the line meets the cubic. And we're told we can use this fact. X cubed, and this might seem a bit like a sort of random fact that's come out of nowhere. X cubed minus x minus m x minus a. So if you stare at that, that's cubic minus the line is equal to x minus b squared x minus c. We don't need to prove this, but I'm going to explain where it comes from. So this says that the difference between the line and the cubic has a repeated root at b, another root at c, and the first coefficient, the coefficient of x cubed, also works out to be the coefficient of x cubed is 1. So there's no prefactor in front of this. That's how I would prove it if I had to prove it. Anyway, we're not told to prove it, so I should shut up and just instead show that c is equal to minus 2b. I think my plan here is to multiply out the right hand side. I want a fact about c. C is hiding over there on the right hand side, and I suppose my way in is that this is just a polynomial, right? It's two different ways to write a polynomial, and what I really want to do when I see two different ways to write a polynomial is to compare coefficients in some sense. That's just always what I do when I've got two different ways to write a polynomial. First thing on the left I've seen before in the question. The thing on the right is new. It feels like they've gone to some effort to tell me this thing. I'm going to multiply it out. So I'm going to get sort of x squared minus 2b plus b squared, x minus c, which is, I think, x cubed minus 2b x squared minus c x squared plus b squared x minus 2bc x. This is what you came for, right? Watching somebody else multiply out brackets. Okay. So comparing coefficients, so I get this x cubed coefficient. Oh yeah, that matches up, that's good. This x squared coefficient is, oh hang on, that's gonna have to be 0, right? So my x squared coefficient, that's minus 2b minus c, must be equal to 0. And great news, that rearranges to c as minus 2b. So that looks like not much effort in terms of what I've actually written down. But the logic there was really that they've given me this fact, I'd like to compare coefficients of these two different ways to write this cubic. So part 5 asks us a kind of follow-up question at the end. This quite often happens in math questions where you've done some calculations and now that you know everything about the setup, we ask you to do some calculation involving finding an area perhaps. Here we want to find the area of R. Okay, and they ask us a bit of a strange question. They ask us for what value of A is the area of R largest, and I don't know if they're expecting me to do that with some sort of geometric argument, or whether they're expecting me to do that by just calculating the value of R. Later in the question here, show that the largest possible area of R is 2704, makes it sound like I should just find the area of R. This is going to use a little trick that I'm not sure how familiar people are going to be with this. But in general, to find the area between two curves like this, like here one of the curves is just a straight line, but to find the area in between two curves, you do one of the equations minus the other. So here you do one of the equations minus the other, and you integrate that. So here I want to do this. And I know, by the way, that m is 3b squared minus 1, a is 2b cubed over 3b squared minus 1, c is equal to minus 2b. So I sort of know everything in terms of b. This looks like it's got lots of different constants in it, but they're all in terms of b. My plan is to just do this integral. I don't know if anybody's got a better suggestion, and I'm actually not going to do it on stream because I think we've got more interesting things to do. But my plan for the rest of this question is do this integral. It will turn out to be, here's some top skills, it'll turn out to be proportional, it's something to do with, it's proportional to b to the 4, which I can sort of tell because I know that things like m is sort of b squared, this x is being integrated across b. Yeah, I just think it's proportional to b to the 4. I've just got this feeling that it's proportional to b to the 4. I suppose we could use the previous part. This is equal to x minus, what is this equal to? X minus b squared, x minus c, possibly with a minus sign. Then it looks a bit more like a kind of b to the 4 kind of thing. Okay, it's 27. Somebody in chat tells me it's 27 over 4 b to the 4. I think I could probably have guessed that. And b is somewhere between minus 1 and 0. So it's not too hard to maximise that for the size of r. Here's my graph. So I think sine looks like this. Oh, that's an okay sine picture. It's not my best sine picture. Livestream 7 had a really good sine picture. I'm editing that one at the moment. So this is 1/2. And I might think about special angles or special triangles. I've got this triangle in mind, right? This one that's like 1/2, 130 degrees up here. Okay, I think that means this is 30 degrees, and I should just probably know this, but I have to think about like the symmetry of sine to think this is 30 degrees away from this 0, so this point is going to be 30 degrees away from this 0, that's going to be 150 degrees. Okay, so the first inequality just means 30 degrees less than or equal to x less than or equal to 150 degrees. Okay, let's think about the second inequality. So now I need to draw a picture of, this was sine x. Now I'm going to draw a picture of sine 2x. I suppose drawing these graphs is a good test for thinking about transformations of graphs, which is on the math syllabus as well. Not sure about this. Okay. I say it's becoming a bit of a catchphrase, but I point at things and say it's not my best picture. This is not my best picture. Okay, so where does this happen? So there's a couple of roots over here where if I think about them, this has been squashed by a factor of 2. So these are probably 15 degrees and 75 degrees. Thinking about how this sine curve has been squashed down, so these solutions have been squashed down to 15 and 75. And then there's a couple more solutions over here at larger angles. So if I add on, I have to add on 180 degrees to get to this bit. I think sort of half of the full interval because it's repeated in there. So that's 195. And this is, oh, do I want to work that out? 180 plus 75 degrees. Not sure I like that. 255 degrees. Okay, great. And that's what I did. So this is 15 less than x less than 75 degrees, or 195 degrees less than x less than 255 degrees. Okay, great. Then I need to read the question, and it says one or both. So I've got my intervals, and I need to think about when you're in one or both of these cases. And I think sticking these together will give me, putting them together will give me 15 degrees less than or equal to x less than or equal to 150 degrees for the first bit, because I go from 15 to 75, then I'm already in this one and I get the rest of this interval up to 150, or 195 degrees less than, so this is one or both, 195 degrees less than x, less than 255 degrees. Okay, got to do some fractions now. So this is, what is this? This is 9 lots of 15. Plus, how many lots of 15 have I got over here? 2, 10, 2, 45, 4 lots of 15 over 360, which is 360 is 3, 4, 15, 30 lots of 24 lots of 15, he says. I think this is 13 over 24. Wow, imagine taking that long to do fractions. Right, okay, I think it's B. I think I've got B. So, approaches to this question. I saw someone in chat suggest that this is the sort of question where you want to turn it into a quadratic, where you want to use facts about sine squared and cos squared to try and turn it into a quadratic in terms of cos maybe, and then use some quadratic science on it to say where this thing is biggest. So I think the suggestion I saw in chat was to write this like this. And then do some sort of rearranging. So I'm going to write this as 4 cos squared x minus 4 cos x minus 5 squared, where I've missed a minus sign on every term, so I'm okay. Okay, so what am I going to do? So I think a way to make progress with this that I've seen before in similar questions is to think of cos x as being the variable here. Cos x, what do I know about that? Well, it's somewhere between -1 and 1. So what have I got? I've got, if I call it u or something, then I've got this, and I'd like to make this as large as possible. And there's sort of a trap here that, we're squaring a thing, and you can make the square of a thing large if this, so we want this to be either very positive or very negative. Okay, so if I want to make that thing inside the bracket very positive or very negative, I should think about this curve, this thing 4u squared minus 4u minus 5. I quite like completing the square. I think I'm going to complete the square just to see what happens. It's this when you complete the square, and that shows me that this is something like u is a half. When u is a half, this reaches a minimum value at -6. When u is a half, and then it's going to be something like this, I suppose. When u is -1, this is going to be 3 squared minus 6. It's 3. This is -6. And when u is 1, this is going to be 1 squared minus 6. Is -5, is that right? Yeah, okay, so it's somewhere down here, -5. So this thing inside the brackets is the most positive it gets is 3, and the most negative it gets is -6. So these are two things that I should check. I should square each of those and check which gives me the bigger number. Perhaps you already know which one gives the biggest answer when you square it. Yeah, okay, so it's slightly interesting that it's the case that we're making, in this particular case, we want to make that the thing inside the square there very negative, because we can make it more negative and we can make it positive. Worth thinking about both of those cases. I think that's the trap in this question. You have to consider what happens when the thing inside the bracket is very negative. Okay, if I make it very negative, then I get 36. Here I only get sort of 9 or something. That's not the biggest possible. So I think my answer is B. I think I can make this 36 by making the thing inside the brackets -6 by putting u equals 1/2. Ooh, is that a nice angle or something? So when is that a nice angle? Yeah, that's like it's like 60 degrees, right? So we're not going to get caught out this time. We've seen that we've got this thing being squared, so we want the thing inside the brackets to be either very positive or very negative. That's not going to catch us out this time. And there's a sort of, we want this thing, all of this inside the brackets to be very positive or very negative. Either of those would give us a big square. Okay, there's a sort of trick going on here that we're thinking about x varying across all the real values, and as x varies across all the real values, 10x plus 11, that varies across all the real values as well. So maybe I could think about 3 sine squared, I don't know, yeah, new variable here, like y or something, minus 7. We want this either very positive or very negative. Okay, sine squared y, where does that go? So if y is any real number, and I know that sine y is somewhere between -1 and 1, but this is sine squared, so those negative values of sine will get squared, and this will be somewhere between, so this thing here is somewhere between sine squared, somewhere between that and 1. So I suppose this 3 times this minus 7 is somewhere between, between minus 7 and, when this is really big, when this is 1, this is -4. Okay, so it turns out we can't actually make this expression very positive at all. We can't make it ever positive, but we can make it very negative. We can make it very negative if we make it -7. That is very negative. If we make it -7, then when I square it, I get 49, which is option C. I don't think I can make it any bigger, and it takes that value whenever, I guess, whenever y is 0, which is, for example, x is -11/10 or something. So the answer is C. Hooray! Let's have a quick look at the live poll. Gradient of the line joining this point. So we're taking a point on the curve, x, y, where, actually hang on, I know that y equals x squared. So I'm going to call this x squared. That's the point on the parabola. X is not 0. Okay, good. Show that the gradient of the line joining this point to the centre of the circle, the centre of the circle is over here at 0, 2. Gradient of the line joining this point to the centre of the circle is given by that. This is testing, do you know how to find the gradient of the line? So this is the kind of, back in my day we'd call this sort of C1, or like the first unit of A-level maths, this kind of thing about finding the gradient of lines. Brilliant. I know that things like C1 is not so much a thing anymore because you don't have units anymore. Okay. With the help of that result that we just had, so that gradient is, that thing was x squared minus 2 over x, or otherwise, so either way, show that the coordinates of B are given by this expression. Okay, so I'm going to find this point B, I suppose using the fact that the circle and the parabola are tangential to each other at the points A and B. So I'm going to use the fact that the gradient here is perpendicular to that line joining the centre of the circle to B. So here I'll say that gradient of the curve at B times the gradient joining B to centre, those things are perpendicular, so that's -1. Now I've got to do some maths. The gradient of this parabola is 2x at that point. The gradient joining B to the centre is x squared minus 2 over x. That's what we did in the previous part of the question. I know that when I multiply those things together, I'm supposed to get -1, so I can solve this, I think, to get x squared is 3 over 2. X is equal to plus or minus root 3 over 2. They don't actually tell us that B is the one with positive coordinates, but let's just assume that B is bigger than A. And if we assume that B is bigger than A, then x is equal to root 3 over 2. Oh, and I suppose the y coordinate is x squared. X squared is equal to 3 over 2. Okay, part 3. wants us to find the area of this circle. Not the area of the circle, sorry, the area of this bit of the circle. Joining A. I wish maybe I should have given the centre of this circle a name, because it's, excuse me, the centre of this circle is coming up all the time in this question. Oh well, we want to find this area, which I think is going to involve finding this angle. But we're already at the point of this question, like we were in that 2011 question. We sort of know everything about this problem now. We know where B is. We know where the centre of the circle is. That was in the question. We know where A is. It's on the opposite point. It's B. We know that's the circle. So really, the parabola is not really relevant anymore. We just know where all the points are, and we want to find that area. Yeah, maybe we should find the radius of this circle. That sounds like a good idea. Let's try and draw that circle. So we've got this point is root 3 over 2, 3 over 2. This point is, what is that point? So this is, if I drop a perpendicular sideways, then I get 0, 3 over 2. Up here I get 0, 2. So I think this side length is 1/2. This triangle is like a right angle triangle. This side length is root of 3 over 2. I really want this angle. This is phrased in terms of arc cos. I think I naturally, if it was up to me, if it wasn't a show that question, I'd probably write something like arc tan of root 3 over 2 over 1/2 or something. But they want me to do it in terms of an arc cos. I think the easiest way to convert between the two is to not convert between the two, and instead find the radius of this circle, so that I can think about this as adjacent over the hypotenuse. Find the hypotenuse of this triangle. I'm going to need to do Pythagoras, aren't I? So Pythagoras, to find the length of that line, that's going to be square root of 1/4 plus 3 over 2. I think 3 over 2 is 6/4. This is root 7 over 2. Okay, so my radius is root 7 over 2. And this angle is going to be theta. It's going to be inverse cos of adjacent over the hypotenuse, root 7 over 2. Okay, where I had to do this step of finding Pythagoras to find that hypotenuse using Pythagoras, just because I wanted to think about cos of the angle. Cosine of the angle is the thing in the question. Slightly awkward. Okay, what do I do next? So I want to think about the area here being, I suppose it's now it's either going to be area of the circle. Area of the circle is going to be pi r squared times, and then I either want to write 2 theta divided by 360 degrees, or if you use radians, 2 theta divided by 2 pi radians. Here I suppose it depends whether you think this arc cos thing is measured in terms of degrees or radians. Back in 2012 the map used radians, so the answer that's being given here is precisely pi r, radius of the circle is root 7 over 2. Square that, pi r squared times, and then 2 theta over 2 theta over 2 pi is just theta over pi. We saw that theta was inverse cos of 1 over root 7, and the pi's cancel out. So, or over pi. So that's what this is. If you use degrees for your arc cos, then you get this extra factor of pi over 180 degrees, which I tried to express in a comment at the top. Part 4 of this question says, suppose now that a circle with centre in A is resting on the parabola, where A is positive. Find the range of values of A for which the circle and parabola touch at 2 distinct points. And I suppose this comes down to thinking about whether that distance between the origin and the parabola, that distance is bigger than or less than the distance from here down to the origin. So whether that distance is bigger than or less than A. I need to find the position of B in terms of A, find the distance from the centre of the circle to B in terms of A, and then for those points to be like this picture in the question, rather than like this for a very small circle, I need the distance there to be less than the distance down to the origin. Okay, find the values of A for which the circle and parabola touch at 2 distinct points. I think those are the two cases, that either the circle rests inside the parabola like this, touching at 2 points A and B, or if it's a very small circle, then it just sits at the bottom of the parabola. Okay, we need to decide, is there space underneath for the circle to rest above the ground, held up by this parabola? Okay, how do we actually do that? Well, I'm going to rerun the previous algebra. Rerun the previous algebra in terms of A. Okay, but I'm not actually going to do that algebra now because we're running out of time. Okay, so I'm planning to just run the algebra now. If you're off, bye. I'll try and do this quickly in case you're staying. Okay, so in general, this is still the picture with A equals 2, but I'm going to say that's A. Then the tangent at B has gradient. In general, let's say that the x coordinate of that is something like. Wait, what am I doing? Yeah, okay. So in general, the line joining B to the center has. I need to redo the part 1 thing as well. The line joining B to the center has gradient this. B to center. Center has gradient this, where that A has replaced a 2, and I want I want this 2x times x squared minus A over x to be equal to -1. So x had better be equal to A minus a half, x squared, A minus a half. Aha! So, yeah, add the A, multiply by 2, minus half, x squared is A minus a half. I see, so that's only got sensible solutions when A is bigger than a half. So I need A bigger than a half. Maybe that's the answer. Let's follow through just to make sure. So in that case, the radius, and we need this for part 5 anyway, but I'm planning to find the radius since that was my initial idea. In that case, the coordinates of that point are root A minus a half, A minus a half, that's where B is, and the radius is, what is that radius? So I need to do the difference in x coordinates squared, A minus a half, plus, and then this is minus a half squared, actually that square rooted, which is root A minus a quarter or something, I think. X squared, A minus a half squared, yep. Difference in x coordinates, difference in y coordinates, square, add the squares, yeah, good. A minus a half, I want to know, and my original idea, which I'm no longer so convinced by, but my original idea was to check if is root A minus a quarter bigger than A, and I think A minus a quarter is bigger than A if this thing is bigger than A squared, so if 0 is bigger than A squared minus A plus a quarter, being a little bit sloppy with my square roots here. So that happens if A is big enough, if A is bigger than, oh, okay, that always happens, because that's just that, isn't it? Cool, okay. So I think I need A bigger than a half for these points to exist, and if A is bigger than a half, then it does work out that that distance is shorter than A. Okay, so I think I said something silly the first time I saw this question, but then doing the algebra forced me to actually check it. And my answer for part 5 is that this radius is A if we're sitting at 1 point, and it's root A minus a quarter if we're not. If I guessed A is bigger than a half, that doesn't sound right because that, oh no, that's good. A is bigger than a half. Sitting at 1 point, A less than a half. Okay, cool. Finished 4 and 5.